Hi, I am Jessy Grizzle, a professor in the Electrical Engineering and Computer Science Department at the University of Michigan. Last week we were talking about MABEL and various applications of feedback control. I promised to answer your questions, so let's get started. So Christopher Pope asked if MABEL, or future versions of the robot, would be capable of lifting heavy loads in the future, being able to help dock workers, etc. So MABEL, the special thing about that, remember, is MABEL had to walk and run in a circle. It has a boom to stabilize side-to-side motion. So the first thing we have to do is get MABEL free of the lab and able to function outside. So what we're doing is we're going to build a new robot. Its name is Atreus. This new robot is going to be a free-walking robot just like you and me. There'll be no longer need for a bar to hold it up from side to side. Should be able to go out on the diag, go up and down the steps at Lurie, do all sorts of wild and crazy things. And once we have that mastered, then surely someone else could invent some nice arms for the robot, bolt them on, and then we could see about doing things like that. The next question was from Tony, and he's asking if the experiments we're doing on MABEL are pretty much replicating similar feedback mechanisms that you find in the human body. Well, let's talk about that. So metal links on robot, that's kind of like bones in the body. Motors on robot, that's kind of like muscles in the body. The wires are kind of like nerves, and the computer's kind of like a brain. So I can see where the question is coming from, but they're still fundamentally different things. So the feedback mechanisms we're using on the robot, they're based upon these detailed mathematical models of how the robot moves, the equations of motion. Whereas the control mechanism in the human body, that's the result of millions of years of evolution. So fundamentally, they are different. Now, it's true, at a very high level, the robot has to keep itself upright. It has to have reflexes to respond to disturbances in the environment and things like that. So yes, there are common elements. There are roboticists who do a lot of work that tries to emulate what biological systems do, what animals do, and even what humans do. But we're more the math tech, geeky kind of guys who work on problems from those fundamental principles. Okay, Jason and Joy want to know if we are working on bipedal robot applications like MABEL for medical reasons to replace worn out or amputated limbs, or if we have even further medical applications in mind. Well, it's true, there are a wide range of researchers that are working on the development of prosthetic limbs, and in particular lower limbs, legs. So working on prostheses is even more complicated than working on robots like I do, because with robots it's all mechanics and electronics all the time, whereas with a prosthesis you have to also interact with the human body. And so they've got the more difficult problem of biomechanics and electromechanics. Now even furthermore, there are people taking this technology, some of it for building what's called an exoskeleton. So an exoskeleton is where you put a mechanical and electromechanical device outside the body. It's not replacing a limb. It can be lower limb, upper limb, torsos, etc. And these give you the power to lift great weights, perhaps walk and run huge distances while carrying 150 pounds on your back, etc. And that's another very interesting way. And of course, it also is like the prosthetic limbs. It has all the complexities of interacting with the mechanics and the biomechanics at the same time. I'm very fortunate. I'm working on MABEL. That's a great problem, but simpler. One of our YouTube viewers, Fosgrafia, asked, what sorts of everyday things do I use where feedback control is an important item? Well, probably the most important one is your car. So your car is full of literally hundreds of feedback loops. So you've had ABS braking systems, I'm sure, which help you if you live in the Northeast like we do and have to deal with ice, etc. They help you brake very quickly on difficult surfaces. But maybe you're also thinking about these more modern cars called hybrid electric vehicles, where you have combinations of internal combustion engine and using gasoline or diesel, an electric motor and batteries. Well, there are many, many feedback loops to regulate how much of the power should come from the internal combustion engine, how much could come from the battery, when do you recharge the battery, etc. Even other applications. How about your cell phone? Ever thought about feedback loops in your cell phone? Well, your cell phone establishes a feedback loop with the nearest tower and regulates the power of its transmission in such a way that you get an adequate sound quality, etc., and uses the least amount of battery power possible. Without that, you'd be broadcasting at the maximum power always to get range, and your battery would last hours instead of days. So, there's even more applications coming in the future. Some of the modern homes have feedback loops in washers and dryers that instead of running for fixed amounts of time, they wait until the clothes are sufficiently clean and cut off. Dryers, that's much more common now. They cut off when there's a certain moisture level in it. There's going to be many feedback systems in the home for safety, etc. So yeah, feedback all the time, everywhere. Thank you for coming back and allowing me to answer your very interesting questions. I hope you'll come back for the next Ask M session. I also hope you'll stay tuned to our YouTube channel where MABEL will be doing some really crazy things, I promise. That's dynamic leg locomotion, or you can just search on MABEL and robot. See you guys, bye.